Thank you. Thank you, Sudipta. And pleasure to be talking here. I mean, you know, the benefit of the crisis is we get to interact with more colleagues than we do normally. So, I'm really welcoming this opportunity to present this recent work. Okay. This is recent work, which is recent to the extent that a formal paper does not exist yet. The slides are precise, but in fact, this is a follow-up paper. Let's see, where is the, this is a follow-up paper to an earlier piece also on fair division, which was in a more general context, although in fact slightly different than this one. I'm not going to go into details. The co-author then included a mathematician. In this particular new paper, it's going to be just Anna and I. Okay. So, so this is really, I would say, classic fair division. I mean, classic as in, you know, first invented by mathematicians in the years shortly after World War II. I mean, you know, the famous paper by Steinhaus in 1948, a couple of papers, and then picked up by a tradition in mathematics, and of course in economics. But the interesting thing I believe about this particular discussion here is that it's a rather non-familiar type of model to do fair division, even though we believe it's a very important realistically speaking. So in other words, what we have to divide, to distribute, are a bunch of indivisible objects. And, you know, these objects can be valuable or not valuable, sometimes typically valuable for somebody, not valuable for somebody else. I mean, there is no constraints there. All these objects must be distributed and consumed. So in particular, if it's all bads, I mean, people have to distribute bads. But critically, money is available for compensation. So indivisibilities, in fact, do not create the type of difficult mathematical question, approximation question that you have when you have real indivisibilities and no means to do compromise, because thanks to money, we can do compromise between the various bundles of indivisible objects. So when I say that this model has not been discussed before, I exaggerate a bit because if you think of the whole literature about the assignment problem, when we have each person will get an object and then we will share the rent if it's a matter of sharing a flat and the rooms in a flat and so forth. But what I'm saying here is that in fact, we will go to a much more general model than the assignment one, as you will see why. And in fact, assignment will not give particularly interesting results there. Okay, so standard examples to illustrate that fair division is a relevant problem in reality, in context of dissolution of partnership, distribution of goods or bads between partners and so forth. Okay. All right, so we will be looking for rules which are easy rules. Easy in the sense of simple messages, and therefore easy to play. And we will not be very sophisticated at all in terms of the strategic implementation. You will see exactly what I mean very soon. So let's start with the two most celebrated and familiar rules that do apply to this context. I mean, there is first of all the classic divide and choose, which works very well here, of course. Meaning what? You don't have in this case to use cash. You could even just do it with a division of the bundles without the cash. But of course, the goal in the paper is to ameliorate, to improve divide and choose without cash by allowing cash, right? So here I'm not explaining what divide and choose is, of course. Another one which is almost as well known, except maybe you don't know it, some of you may not know it under this name, is so-called Texas Shootout. Texas Shootout is actually something very simple and discussed in the econ theory literature, is the situation where you have two partners in a joint venture which they own with equal rights, and then one of them wants out. That is to say, he wants to get rid of the partner one way or another, and the two ways are either from the partner, or he himself is paid to leave and leave the full venture to the partner. So in other words, in Texas Shootout, one of the partners make a cash offer, and the other partner can either accept this amount of money and give the entire venture to the first agent, or this other partner who receives the offer can simply say, okay, I will buy you out from this venture with this amount that you just quoted. So we will see, I mean, that this corresponds, as kind of obvious, to a fairly simple bidding game. Okay, so again, you know, the common feature, simple message, which both require small cognitive efforts in the sense that you don't need to formulate complex preferences even to know about them. And to me, the absolutely very strong evidence of that is the fact that, you know, things like divide and choose, you can have children of basically the age where they can speak to play the game. And they have absolutely no issue doing it. And of course, they don't need to make some complicated effort. So the message is very simple, and you reveal very little about your preferences, assuming that they are fully formed and complex. So in the context where we divide objects which could be good or bad, and you don't want to really reveal which ones are good, which ones are bad, this is very important. But we will not elaborate on that in any formal way. Okay, and then it's going to be a case, the goal here will be what can be called worst case implementation of fairness. We want rules in which everybody has a strategy such that no matter what other parties do, you guarantee a certain level of fairness to be defined shortly, of course. So no, we are not looking at strategizing and what could happen if you try to learn something about the preference of the other agents. Of course, if you are able to do that and you gain some information, then you can take advantage of it. But typically, it will involve a risk in the sense that if you were wrong in your collection of information, and in fact, you got it wrong, I mean, you could actually end up losing vis-a-vis that benchmark of fairness that we will be after. Okay? All right, so that's the context. So Texas Shootout with N agents, what is it? I mean, I take this as the first example because it's the simplest that involves money. It's simply, it's simply the rule in which we decide to allocate the whole mana, the set A, I didn't introduce that yet, but A is the set of all the indivisible objects. So we allocate the whole bundled mana through an auction. Everybody bids how much this mana is worth, and then you split the winning bid equally between all agents, including the winner. Therefore, the safe bet, the safe bid, if you are an agent for whom the mana is worth X, and you know that you are sharing it with N agent, your safe bet is X, because if you win, you will have to give away N minus 1 over M times X. And if you lose, someone will give you at least x over n. So you end up by this simple and very well-known bet to guarantee to yourself 1/n of the value to yourself of the entire mana. Okay, so if there are any questions about the interpretation or explanation of that rule, please raise them now, because you see, I will not need to go beyond that in the analysis of that rule. We understand that this may end up with something not efficient if people don't play truthfully and so on and so forth. In fact, well, okay, so I'm not going into that because we can come to it through questions, but essentially this is not the topic here. Okay, now some criticism of this idea of simply auctioning the entire bundle is that this is actually not very efficient in the following sense. I mean, just passing the bundled mana is not a good idea. For instance, if utilities are subadditive. I mean, there are certain contexts, typically when utilities are superadditive, where it could be the efficient, proper way to allocate the entire mana to a single person. The fact that utilities are superadditive per se is not enough to guarantee that, but if utilities are superadditive and the situation is symmetric, then yes, it's going to be efficient to give everything to the agent who has the highest value for the mana. But then if utilities are subadditive, that's not a good idea. And because you're going to lose a lot of efficiency, and this is exactly what divide and choose is able to do, is that at least the divider who proposes the division can adjust to the situation, whether he is subadditive or superadditive, and therefore go further toward efficiency. Okay, so what we're going to do, the first part, one first contribution of the talk, not very complicated and perhaps not extremely original, although I'm not sure I've found it in the literature, but it's to explain why in the context with monetary transfers and simple linear utility vis-a-vis money, there is a simple way to generalize divide and choose, and also, of course, to adjust for the fact that divider and choosers have different roles. I mean, to bring symmetry between all the parties. So we will do that. That's going to be one type of rule. Okay, so we will discuss what we can call the fair version of divide and choose for n agents when there is money. But then we will also introduce a new family of rule, which we call the bid and choose rule, which have some advantages vis-a-vis divide and choose, in the sense that they ask you to reveal less than divide and choose. But then also they give more flexibility to the manager. So they are not actually a single rule, but a family of rules. And we will compare the two in that spirit. I mean, not trying to say, of course, that we are exhausting the realm of simple rule that could be applied here, but these two seem to emerge. Bid and choose, we have not directly seen in the literature. I mean, it was already introduced in our previous paper in a slightly different context. Okay, so here is the model. Here is the model. Very, very simple model. That's what I like about this, is the fact that you know, mathematically, the mathematical environment is extremely transparent, I mean, and simple, which doesn't mean that you don't have difficult open questions, but at least to read what you are doing. Okay, so you have a set A, a finite set of objects. Capital N is the set of the n agents. And what we need to do is to pick both a partition of the object, right? So capital pi will be for partition. SI is the share of agent I. And then also a set of cash transfers, TI, which sum up to 0. The fact that they sum up to 0 is more of a sort of normalization than anything else, because it could be that you also have, like, for instance, in the case of the rent, sharing the rent of a flat, it could be that the sum is imposed, like the sum must be corresponding to the total rent or some negative or positive number. That wouldn't be important because of the key assumption that utilities are quasi-linear. Of course, we are not going, although one could, but we are not trying to go into more fancy preferences in which utilities are simply increasing in money. I suspect you could develop the theory there, at least some steps of it, but it would not be that simple. In this context, with everything quasi-linear, things are much more amenable. Yes, Indra?
Yes, just to clarify, S is the share of the whole bundle, right? I mean, S1 is the share of the whole bundle that agent 1 gets.
Yes, yes. The partition pi is the partition of A, of capital A.
Okay, okay. No, I mean,
so
earlier you mentioned debundling, so you're not talking about debundling. You are not sharing each object.
No, but by debundling, I meant if you look at the Texas shootout, I mean the auction for the whole mana, that was the bundle. You know, nobody can get a subset of the object. You get the whole thing, or you get cash, one or the other. Here, as in divide and choose, it's perfectly fine that you get a small subset and then the other person gets another subset and so forth. And in fact, if you think that you are in a context where utilities are typically subadditive, then it's obviously a better idea to allow small shares. So indeed, here, full liberty, full freedom in choosing the partition, right? Absolutely full freedom. And cash transfers, of course, also no constraints. I mean, so, you know, no income effect. That's okay. All right. So still, of course, utilities are quite complicated combinatorially because for each subset of capital A, you have potentially a different number. We will put some restrictions to interpret the result and to adjust some results, but fundamentally the whole theory works without any restriction on these utilities. So it could be quite complicated. It could be that, for instance, one of the objects brings positive externalities when you add it to a certain bundle of other objects. So adding that A to a certain bundle increase the value of the bundle, but then adding it to another bundle could decrease the value of that bundle. As in, you know, you are forming a team of players, a team, and then, well, this person works well with that group of people, but with this other group, they create some bad vibes, miscoordination because they just don't understand each other, etc. So that's the potentially the context, and I will specify a couple of special contexts that we can look at. So in this context, in this model, as is well known, but it's important to remind it to be sure that what is an efficient allocation? An efficient allocation of the object, efficient in the sense of Pareto optimality of the entire economy, objects plus money. So efficiency means that you have to distribute the object in a way which maximizes the sum total of those monetary values of the share. So on the one hand, you are just maximizing this sum, the sum of the UI SI over all partitions, irrespective of cash transfers. And then whatever cash transfers summing to 0 you perform, they do not affect efficiency. They are just there to, in fact, enforce some fairness criteria. And this is why that context is so nice to study fairness, it's because you have a complete separation of, on the one hand, efficiency consideration, on the other hand, fairness issues. So that's very nice. I mean, yeah, it's a bit exaggerating to say that the fairness only comes from the cash transfers. I mean, of course, it's influenced by the division of the shares, but okay. All right. And just like for the divide and choose Texas shootout, I mean, for the more complicated rules that we will define, they will not deliver fully efficient allocations, right? I mean, they will, by a simple process, give something which is not efficient, and we will not try to measure loss of efficiency or something like that. We are just concerned by implementing some fairness, but also by defining. The interesting question here is, what do we mean by fairness in such a general context? All right. Okay. So quickly, domains that will be of importance. There is one domain which, domain that is to say, it's a subdomain. Huh? It's restrictions on the utility function U, which makes sense and which help with some results. The first one, which we like because in a sense it's very realistic, it's the one where each object is either good or bad. I mean, for a particular agent, the same object could be good for one agent, bad for another. But if this object is good for this particular agent with utility U, it means that adding A to any share S, possibly empty, is weakly an improvement. And if the object is bad, it means adding it to any subset is weakly a decrease of your total utility. Okay? And that allows you for each person to split the object into positive, negative. Of course, you could have objects at the intersection who are both, but that's absolutely not important. Now, the other two domains, which are not directly linked to the mixed monotone, are the subadditive and superadditive domain. Huh? So there, the definition is absolutely standard. Subadditive is that the sum is worth less than the value of the whole of the union is less than the value of two disjoint subsets. And superadditive, the opposite. So roughly speaking, but of course not exactly, this corresponds to either decreasing marginal utility or increasing marginal utility, or equivalently decreasing marginal cost if we are talking of task. I mean, those are very well-known notions, so I'll be quick, of course. And then potentially there is also the full general domain, which includes everything, where you have no restrictions. But the difference between subadditive, superadditive will be very, very critical here, as you will see very soon. Okay. So a partition, well, I don't know why the slides repeat what says before. The partition is again pi. Notice, of course, that's quite important. Shares can be empty. It's perfectly fine to say, I take everything and I give, for instance, if you are the divider, you could say, oh, I want everything and I'm going to give so much money to each of you, which of course I pay from my own pocket. So you could act as in the auction for the bundled mana that we looked first. And then what here, just for notation, we speak of partition, and then compensated partition is going to be both the shares of the object and the vector of transfer summing to 0. Okay? All right. Simple lemma. That's a very simple algebraic lemma, or not even that. If you fix a balanced vector of transfer for each agent 1 to n, then there exists an assignment of 1 to n to the agents with a non-negative surplus. What is that lemma? It's something extremely simple. So here is the illustration, which is also a proof, you will see. So you have these 1, 2, 3, 4 object. In fact, in a moment, these things will become shares of object. But for now, it's 1, 2, 3, 4, the numbers. And then you have these 4 agents, 1, 2, 3, 4, who each of these agents is proposing a vector of balanced transfer. So for instance, agent 1 is saying object 1, no transfer, object 2, I give away 3, object 3, I take 4, or I give away 1. And they have to sum to 0, all of them, right? -4, 6, -1, -1, etc. So now what I'm saying is because the sum of those 4 rows is 0, so is the sum of those 4 columns, right? That's the proof. Because the sum in total of all the coefficients is 0, the sum of the 4 columns is 0. So therefore, there is at least, sorry, no, wrong. Wrong, I need assignment. I take all the possible assignments of 1, 2, 3, 4 of the rows, of the columns to the rows. So for instance, on the diagonal, that's one assignment. Or this one to this one, this one, this one, and this one, okay? Or and, tank, tag, and this one. You know, like when you compute a discriminant, a determinant of a matrix. So they are what? They are factorial for assignment, right? And their sum is 0, right? Because the sum of the whole, the coefficient is 0. So therefore, there is one assignment where the sum is negative or 0, okay? For instance, what is relevant here is to look for which assignment given the matrix gives you the most negative number, in other words, the smallest amount of transfer where transfers are taken to be positive or negative. Because here the interpretation will be when you have a negative number, it means you are willing to give away money. So by looking for an assignment where there is a very negative thing, you look for a situation where agents are willing to give up quite a bit of money collectively, and therefore you can redistribute more to each and get closer to efficiency. So here, for instance, if you look at this particular matrix, you will see that by taking this assignment where column 1 to row 4, and then column 2 to row 1, and then here and here, you get a total negative sum of -9, which is the max for this. Okay, so now how is that lemma used for divide and choose? So divider picks a compensated partition, right? So it picks a partition with a set of transfers, right? And summing to 0. Then each chooser, each other agent except the divider, picks balance transferred over the corresponding to the shares, just the shares of A of objects proposed by the divider. So essentially, just like in the previous slide, you are saying, you know, oh, if you give me S1, well, I'm okay. I could take S1 with no transfer, but if, and so on and so forth, right? So everyone does that. Then the rule will pick an assignment with the largest surplus, and here by surplus, I mean the negative amount. So the smallest sum of transfers, because throughout the transfers can be positive or negative, negative when you give. And then you assign the shares accordingly to agent K, you give the sigma of K, the share SK, which corresponds to a column, you give to the agent sigma of K, corresponding selected by this assignment. And you have a surplus, so you do what you want with it, but in this context, of course, it's completely natural to say that you distribute equally the surplus to achieve balanced transfers, okay? In fact, in this theory, when we are really concerned by the basic fairness implementation, you know, what's the guarantees that you give to each agent, it will not matter at all what you do with the surplus, because in the worst case analysis, you are always thinking of cases where there is no surplus, right? So the surplus will be a bonus in reality for those methods, and it would be interesting to explore, you know, numerically and so forth, how good they are, but that's not what we are able to do here. So here I'm doing another example. Now you see it's the same table as before, except I've put the shares offered by the dividers on top. And then here, these are different numbers, but the star corresponds to the maximal surplus, I mean, the lowest surplus in terms of negative number of -7. And therefore, you can redistribute 7 quarters to each and have what? So far, I've not said anything about what this thing is supposed to achieve, because I'm just saying, okay, it's possible to do those, to list, each one list transfers which sum to 0, and then we give to everybody a share which is worth at least, the share with the transfer, right? So therefore, here is going to be the strategy, the safe strategy of each chooser. Each chooser is going to, once he's informed of the shares S1, S2, S3, S4, he's going to propose transfers which for him make those compensated shares plus transfers equivalent in utility terms. So the idea is, okay, there is this division here. Let me propose transfers such that in effect, no matter which share you give me, it's going to be the same utility. So the same utility, which will be the average of the total utility I get if I was able to consume U of S1 plus U of S2 plus U of S3 plus U of S4, okay? So that's the safe strategy of the chooser, because the chooser has no idea who the other choosers are. He's just looking at the shares proposed by the dividers. So now he plays it safe by making sure that the shares plus and similarly, the divider, as we know already from classic divide and choose, is proposing things. Notice I was using number 1, but in my example here, I should think of the divider as number 1 because somebody has to be the divider, right? So in fact, it was number 1, the divider, who proposed S1, S2, S3, S4 with those transfers such that all the shares plus transfers give him the same utility. And then the three choosers propose their transfers so that they are indifferent between the share S1 and this transfer, S2 and this transfer. I hope this is clear. Please interrupt me if it's not. And now let's compute what they actually are guaranteeing. Well, look at the divider and start this equation from the right. He can choose any partition, so he's going to choose a partition which maximizes the sum of the utility as if everybody was of the same utility as him. So he's going to say, okay, let me choose the partition such that my own utility, I'm player 1, U of S1 plus U of S2 plus U of S3 plus U of S4 is maximum, right? And I'm going to be able to guarantee 1/n of that. Why? Because I'm going to propose transfers such that effectively U of Sk plus Tk is independent of K. I'm going to make all these shares equal. And remembering that the sum of the Tk is 0, it simply means that each term is equal to this maximum divided by n. Okay? So it's a very simple, completely trivial max-min operation. Choose the best partition such that after that you minimize, but in effect you are giving yourself, you are securing for yourself 1/n of the max of those of what we call it's the total efficient surplus in an economy where I would be representative of everybody's preference. Everybody would have the same utility as me, okay? And for the chooser, the guarantee is computed almost in the same way, but except that now, instead of starting from the max, you start from the mean. Because remember, what we're going to be interested in is what is the quantity we can guarantee to a chooser when this chooser only learns his own utility and the number of participants, but nothing else, right? And so that's the key. That's the key of the fair share idea that we will come to in a moment. Namely, the fact that I propose to you something which is totally safe in the worst case. So the worst case for the chooser is that the partition proposed by divider is in fact the one that has the lowest total utility for him, the chooser, right? So he must not count on a partition proposed by the divider that would give him more than that, because this could happen, right? But then once this partition is offered, he, the chooser, adjust with transfers summing to 0 in such a way that each share compensated is worth the same thing, and therefore it's worth 1/n of this mean, okay? So this is the max-min, min-max, in some sense, duality gap of this theory, but it's not, be careful that it's not the max-min, mix-max of the Lagrangian theory of the two-person zero-sum game, because in this theory, actually, min-max is lower than max-min, okay? You will see, oops, sorry. Okay. Fair share. So let's think of just to repeat this, because this is really the key definition in a sense, and that's really the object we are after. It's a fair share guarantee. What's a fair share guarantee? Given the set of objects, given the number of parties in the division, and given my own utility, this is going to be a utility level, of course, involving a share and some money, perhaps. It's a share such that this agent with utility A can secure through a specific division rule, which implements this guarantee, irrespective of who are and what do the other n-1 parties, right? So it's really your worst case level entering the mechanism when you only know your own parameters and the number of parties that you have to know. And notice that by construction, we have built-in anonymity. Where, in other words, it doesn't depend on the index of the agent. So you could, so therefore, it corresponds to a situation where agents have identical rights on the mana. And a natural question is to ask, rights were not equal, you know, somebody is entitled to 30%, the other 20, etc. And that's a very good question. Unfortunately, very, very difficult one. I don't have time. If you want, we can discuss it later, but it's a horribly difficult question, that one. But anyway, let's keep that for now. We stay in the anonymous case. Of course, the feasibility is really what we need. I mean, it would make, you can always promise the sky to everybody and then not be able to deliver. I mean, that's not what we are interested in, right? So we need to have something such that, yes, there is a rule where you can guarantee it, and in particular, it is feasible to do it. So really the key question is whether the sum of these guarantees for any profile U1, U2, UN will be below the efficiency frontier. That's really what it is about. Okay, and we already have encountered one such guarantee. That was the one implemented by the auction, you know, the Texas shootout type thing, which is 1/n of U of A implemented by that rule. That was a nice, very good example. But now let's try to be a bit more general. So these are two general facts. Simple. well, one of them is simple, and they apply to any non-atomic problem of fair division. What do I mean by non-atomic problem of fair division? I mean, it's a problem in which there are no indivisibilities. So if you give me two shares, whatever we are dividing, and here I'm potentially talking of something a bit more general, like in this other paper that was mentioned in the first thing, the one we did before with Richard Stone. So you have a situation in which no matter if consider two possible shares for an agent, there always exists by continuity a continuous line of shares going from one to the other, such that my utility moves continuously from utility from one to the other, right? So it's basically you eliminate indivisibilities. And here, even though, yeah, there are those indivisible objects, but since there is always money and money is perceived in a linear way, no matter what two shares you give me, by performing a transfer of money from one to the other, I can go from your utility for one share to the other continuously. There is no real issues of indivisibilities in that sense. So in such model, I mean, in this general type of model, max mean is the best possible guarantee in any mechanism. And the argument here is the unanimity argument. Unanimity, so I'm applying, of course, to this particular model without trying to be more general, but it actually applies more generally. But here what I'm saying is, okay, suppose I'm able to give you this guaranteed gamma UNA, and that is feasible. So in particular, it has to be feasible when everybody has the same utility as you. So if you have a profile where you have n copies of the utility U, then it must be that each of them can get gamma UNA, okay? But that means that in that particular economy, the word we can think of as the unanimous economy, I am distributing by some partition a sum of the U of SK, which is worth at least n times this, right? In the unanimous economy, what everyone receives is a share U of SI, and the total distributed is the sum of the U of SI for some partition, right? And the total distributed is n times the same guarantee. So therefore, this guarantee that you are promising to enforce is less than 1/n the sum of the utilities at some partition. So therefore, it's less than this number, right? You would say, I mean, it's I can repeat if you think, but it's if you need, but it's a really simple argument. Yes,
it's fine. Yeah. It's fine.
It's a yeah.
Yeah.
So now, what is a less obvious argument, not in this model, but in the general model, the general non-atomic problem, is the fact that min-max is weakly lower than max-min. That's obvious in our model because you have the mean and you have the max. But it's also a fact that it's always feasible. Okay. Now, you will see, I mean, you know, this is, how do I prove in this model, the one I'm talking about now, that min-max is feasible? Well, by the divide and choose for n agent that I just discussed. This divide and choose method that I just described, we showed that it allows the divider to guarantee this max min, and it allows the chooser to guarantee this, because we were talking the absolute worst case for the chooser. So therefore, this is feasible for the chooser, and at the same time, the max here is simultaneously feasible for the divider. Of course, non-anonymous. I will correct that in a second. But okay, so that's a simple fact in this model that the min-max is actually always feasible. in the previous paper that we did with Richard Stone, it was in fact a very painful and tough mathematical result to show that indeed the min-max is feasible. I mean, so you can refer to that paper if you want to see how by using, algebraic topology tools, it can be proven that, and this is more in the general sort of cake division model, it can be proven that min-max is actually feasible. But here in the model of today, it's not a tough statement. Okay. And here I recall, for those of you who know the recent literature on division of indivisible goods with no money, that where typically you assume additive utilities, then you may be a little confused with what I'm saying here, because there the max min is less than the min max. I mean, so you have if you have additive utilities and no monies, where essentially between the min max and the max min, you have the 1/n of the total sum, then it becomes inverted. But forget this. I mean, this is a small, okay. So in some small domains where utilities are sufficiently similar, it's possible that max min is actually a feasible guarantee. That's possible. And if that's possible, that's great, because it means that you have found the best guarantee you can ever give to anybody. Your problem in terms of, what does it mean to be fair by protecting the welfare of the participant, your problem is solved. I mean, you have the best way to do it. So for example, if all utilities are super additive, then very easily to show that the max of this expression here, because of super additivity, is precisely obtained by having a single share of A and all the other shares empty. So therefore, your max min is 1/n ui of A. And that's feasible. It's feasible to give that to everybody, because you just give the object to the person for whom the number you have A is the biggest. And then you can perform transfers such that everybody gets that level. That's a kind of a one-liner. So if utilities are all super additive, fine, we are absolutely fine. If utilities are all subadditive and n is, and there is more agents than object, which is a restriction here, then in that case, you can show that the max min is going to be the opposite operation. Instead of bundling your maximum, you debundle as much as you can, which means effectively, since you have more agents than object, then you give one object to as many agents as you can, and the other have nothing. So you compute in this partition where you give one object per person plus nothing for the other, who just get cash. You do your appropriate transfer, and that happens to be the max min, and it is feasible by the same sort of proof as in the little lemma about assignment. So you have simple cases like that where finding the max min is no problem. But typically, that's not the case. And here is, in some sense, a key type of example is to realize that as soon as you allow for utilities which are more diverse, in particular, if they involve both superadditive and subadditive agents, then it's no longer the case that you can enforce max min to everybody. And here is a very simple example. So we will have 3 identical goods, 2 agents. So the first agent here is a superadditive agent, because for him, one good brings you positive utility of 2, 2 goods 8, so an extra boost of 6, and 3 goods 18, so the extra boost is of 10, so it's clearly superadditive. And therefore, what is his max min? As we said just a minute ago, the max min obtains by claiming the whole bundle and proposing a transfer of -9 to the other agents, giving 9 units of cash to the other agent to guarantee a max min of 9. But if you do the min max, like this agent is in the position of chooser, And then the worst that could happen is that the other is effectively proposing a share of one good and a share of two goods. So therefore, the sum of the utilities for this agent is going to be 2 plus 8 divided by 2, that's 5. So you have this big gap. For the subadditive agent, for him, the first good is worth 10, then the next one adds 4, and the next one adds 2. The max mean will be obtained precisely by debundling, so one good or two goods. Total utility of that 1 plus 2, that's 24 divided by 2. So this agent guarantees 12 if he's the divider. If he's the chooser, he guarantees only 8 because he gets somebody who offers him a full share or money, and therefore the worst that could happen to him, I mean, he cannot guarantee more than 8. All right. And now the observation is that to give utility of 9 to the superadditive agent and of 12 to the subadditive agent is not feasible together, because the total surplus is only 18. I mean, you have two options. Either you do 3 goods like this, or you do 2 goods for one and 1 good for the other. So 14 plus 2, that's 16. 10 plus 8, that's 18. Well, so your total surplus is 18. So you cannot achieve 21. Okay. All right. So that's the thing. And now this is the puzzle. What do we mean then by fair share guarantee? Because max min is not possible, min max is too little, we can probably do better. So where are we? Okay, so the next example I will skip. It's an example where there is utilities are neither sub nor superadditive. Well, I mean, let's do it very quickly. A, B, C, D, 4 objects, 2 agents. So the first agent likes A, B, or C, D. Anything else gives him no extra utility, and anything more gives him no more than 10. Anything less gives him only 0. So the only way he gets utility is by getting A, B, or C, D. And the other agents, the only way he gets utility is by getting either the combination AC or BD or more. And then you have a big gap, even bigger gap between max min and min max, and again the thing is not feasible. Okay, so now I still have what, 8 minutes, 9 minutes about yeah. Okay, so divide and choose, in which we remove the divider's advantage. Well, that's very easy. I mean, there are several ways to do it, but simplest one is an old trick that goes back to the fair division literature in econ context, simply to auction the role of divider. Okay, so the rule becomes a bit more complicated, you could say, because first you have a bidding stage where you say, okay, this is how much I pay to have the role of divider. And how much will you bid? Well, and again, how much will you bid if you are a safe, worst case maximizer type of agent with maximal risk aversion? You know that if you win, you will be able to reach your max mean. You know that if you lose the auction, you will only be able to obtain min max in the subsequent divide and choose play. So therefore, if you bid exactly the difference between the two, and you bid the difference between those two numbers, and the rule being that if you win, you're going to distribute n minus 1. You're going to distribute 1/n of that difference to everybody else and keep 1/n for yourself. And if you lose, someone is going to be offering you at least 1/n of that difference to be the chooser. So it's very easy to check that by this bid, you guarantee exactly 1/n of your max mean plus n minus 1 over n of your min max. Okay, so it's much closer when n is large, of course. Unfortunately, it's much closer to being a chooser than a divider. Okay, so all right, so that one here is now feasible in the full domain. Here now I do not need any more restriction, because you remember that both the max min, min max, I mean the analysis of the divide and choose was correct in the full domain. You didn't use any assumptions on sub or superadditivity or the fact that goods are objects are good or bad. So this is totally feasible, and it's one possible guarantee for the general problem. The question is it a good guarantee? I mean, could we do better? Could we do much better or better sometimes? And that is a tough question. For instance, I will not go into any details, but it can be proven that if you have only two agents, if n equal 2, so you are just halfway between your max min and your min max, then there exists no feasible guarantee such that for every utility u, that feasible guarantee gives you at least this one. And sometimes for at least one utility, it gives you slightly more. So you have a maximality property of this guarantee, the 1/2 max min plus 1/2 min max. I repeat, it's in the case of n equal 2. So it's one guarantee that cannot be improved. It's not the only one that cannot be improved. There are others which are sometimes better, sometimes worse, but at least 1/2 max min, 1/2 min max cannot be improved. However, it can also be shown that for n greater than or equal to 3, this is not true. You can show it's not a very pretty proof, because it only shows you how to improve the thing in one particular utility, but you can define maximal feasible guarantees in which agents get at least that and sometimes more. And to characterize an undominated guarantee above that is a typical open question, which I think is very tough. Well, at least it's very tough for me after giving some thought for some time. I mean, you know, this is really a kind of very tough question. Okay, so I have used a lot of my time, but that's okay. Do I have 3 more minutes? Yeah, 3 more minutes. I will explain very briefly this other family of methods, but I will not. Well, okay. It's the so-called bid and choose rule. And what they have, which makes them specific really, is that the mechanism, the designer chooses a certain price vector for the object. So you can think of it as a kind of a market value estimate. The idea is we're going to give you objects, and we would like you to, because, you know, agents, when they are formulating how much money they want for this and that object, they could be a little bit irrational. And this is something that's observed actually empirically, that, you know, you divide the heirlooms between people, and somebody who is completely focused on some trivial object for some emotional reason bids very high on it and ends up with a share which is of objectively very small cash value, and this creates problem when the stakes are high, right? So in a sense, these methods avoid that, because they ask you to pay for your share in those terms. So here is the way it works. In round 1, each agent bids how much to be able to choose his or her favorite share. And the highest bidder wins. And what can the highest bidder does distribute her bid to the other, 1/n of her bid to everybody else. That's the first payment. But there is a second payment, which is to pay for the share that she chooses. So here it's a standard linear price, and so P sub SI star is the sum of the price of the object in her share. Okay, so she has to pay that, and that bid, that price of her share, is distributed in equal shares to everybody else, including herself. I mean, the usual thing. And then, so in the first round, you are sure to assign one share to the first agent, to one agent, to the agent who wins the auction. And then in the second round, you have a smaller set of objects, smaller set of agents, you repeat the process. So again, because I went too slow, I have no time to go through the computation of the guarantee to that method. It's not very difficult. I mean, it's not trivial, but it's not very difficult. But the one thing I want to show, I want to mention, not showing, is the fact that this is a method which happens to favor subadditive utilities and penalize super additive ones. And, you know, in the sense that, you know, if you have subadditive, you will get something better than the bundled division, the share of the bundled mana. And if you have super additive, you will get something worse. So it's something that goes in the direction which is natural for the balance between super and subadditive, right? Otherwise, I mean, the whole discussion of how you should choose this price, for which there are some results in the slide and in the paper to be, will be is still to be tested numerically and experimentally. I mean, there's still a lot of work to do. And I just want to conclude by saying that even though, you know, we have some concrete result for some concrete and relatively simple rules, there is this really exciting and difficult, I think, to me at least, mathematical question, which is the issue of trying to characterize the family of those maximal guarantees. I mean, the conclusion being that, you know, you start with a problem in which you try to define a basic notion of fairness, exactly like Steinhaus was doing by saying, okay, what's the fair share? Well, it's 1/10 of the value of the cake. So here you try to be more sophisticated, but then you realize that there are several options, not comparable directly, and you would like at least to understand what are the terms of choice, you know, where can I choose my guarantee function? And therefore you are interested in finding those maximal ones, the ones that cannot be improved. And essentially, apart from some simple result for the case of two agents, where you can show that both the divide and choose and our family of methods produce some maximal guarantees, for anything 3 and beyond, we know absolutely nothing. we cannot describe, except of course in some very small domain, but in a rich full domain, we cannot describe a single maximal guarantee function, and that's you know, that's a nice and difficult question. Okay, sorry for going over my time. Thank you.
Thank you, Herve. As usual, your talks are very clear, very nice. So thank you very much. And
thank you.
If you have a little bit of time to hang around, everyone can switch on the cameras and we can take a few questions.
So the floor is open for questions.
And yeah, for people to chat and so on.
So I would probably like to start with a question of my own.
All right.
So in your model, what I understood is there is an implicit assumption that everyone has an equal capacity of claiming.
Yes.
So, I mean, does your model, I mean, work in case of, let's say, let's say, inheritance, when the inheritance passes on with a certain kind of gender constraint. So in that case, let's say in social or legal context, like the claiming capacity of the boy is not the same as the claiming capacity of the girl, kind of a thing. Either it's socially or legally. So in that case, does this work?
So do you refer to a situation where one claimant is entitled to 60% and the other 40%? For instance, or is it something more subtle? Because the one usual way people discuss unequal right is saying, okay, I mean, you have two heirs and they have different shares. Is that what you have in?
So I am saying that there is a natural ceiling of claiming. So the capacity to claim, so the chooser who is choosing has a certain ceiling of choosing. I mean, the chooser cannot go beyond a certain distribution, or it's a constraint set. So in that case.
So that would be like a constraint on the set of objects you can end up with. I mean, yeah, I'm trying to understand in what way it would be formalized.
Yes, it's a constraint on the set. Yeah.
Oh yeah. That would be tough. It's interesting, but it's tough. The type of generalization that we have been trying to think about, but with really little success, is the more, in some sense, clean one where you have 60%, I have 40%. So there, this is the stuff that the traditional cake division literature does discuss. And as you probably know, if you have seen what is done there, it's both simple and not satisfactory at all, because what you are saying is, okay, you have 60%, I have 40%. So let's make that a division of 5 shares of 20%. And we're going to play divide and choose, and you will be playing for 3 people and I will be playing for 2 people. Yeah. So, okay, you can do that. The problem being that now if our share are 3/17 and 14/17, then we have to divide in 17 shares, and the thing becomes quickly unpractical, and it starts resembling these things, this incredible and wonderful mechanism, but very theoretical mechanism that invented to implement envy-freeness in the context of cake division. When I mean cake division, I mean the model where everything is linear. I mean, my utility is an additive measure on the cake and so forth. So at least if my utility is additive on the cake, and I give you 60% and you and me 40%, I know what your fair share should be. It should be 0.6 of your utility for the cake and so forth. That's simple. But now, if I try to generalize and say, okay, now utilities are not additive, and I want to translate that in some ways. So the only thing I can do easily, because that's a very simple modification of the auction, is to assign the object bundle. So 60% of the value of the whole object, of the whole mana, 60% of U of A, and me 40% of U of A. It's very simple. You do a bidding between the two of us, where the largest bid, wins. But when my bid wins, I give you 60% of my bid and I keep 40%. And when your bid wins, you give me 40% of your bid and you keep 60%. And you can adjust that with N people. That's very easy. So that's fine. But now if you want to say, oh, but let's be a bit more subtle and allow for unequal shares, now it becomes very tough. And frankly, we don't know. We don't know exactly which way to go. I think it's a very interesting open question, really. I mean, there may be some, we don't know. I really don't want to say anything. I mean, because I could only show a couple of failed attempts of reaching anything. So, but yeah, it's a good. It's actually, I think it's a really important avenue for fair division these days to be more grasping more the situation where rights are complex, because of course in most situations, in most inheritance contexts, there are constraints, all kinds of constraints. Yes, yes, absolutely.
Thank you. Thank you.
Yeah,
so
another
other
question.
questions?
There is a question in the chat by Conan. He has a 3-part question. You can see it.
Okay.
You want me to read it?
Let's see. How do I?
The chat is at the bottom.
Yeah. It comes because sometimes it. Where is it?
Let me read the questions.
Yes.
Okay.
Yes. Go ahead.
So Conan says, "Thank you for a beautiful talk. 3 questions. How would the results be affected if agents have unit demand? Would the results continue to hold if we restrict to the positive orthant? And then, does the fair share mechanism satisfy the conventional identical preferences lower bound axiom?"
Okay, so assignment, then positive orthant, and then the third question was?
Identical preferences lower bound axiom, is that satisfied? Does the fair share guarantee satisfy that?
Okay, so yeah, the fair share guarantee, which the fair share you can compute by looking at this identical preference situation, is precisely the max min. Okay, so if you are in a lucky model where max min is feasible, everything is fine. But in the model I just described, it's not. Okay, so we are very used. In fact, I contributed to that, and it was for me kind of a axiom, something I believed for a long time, that I mean, fair share guarantees interpreted as the unanimity level. Let's all have the same utilities and compute what we can guarantee to everybody in that context. That would be the solution. For instance, if you are going into Arrow-Debreu commodity, you divide Arrow-Debreu commodities, the standard fair division of variant, folly, and so forth, and preferences are convex. Then it's easy to check that this unanimity guarantee corresponds to getting 1/n of every commodity. I mean, 1/n of each good, each divisible good, and this is feasible. So therefore, that's the best. But as soon as preferences are not convex, if you have an Arrow-Debreu type economy, but except that some people have convex monotone preference and the others have non-convex monotone preferences, then it's no longer the case that you can necessarily guarantee 1/n of omega to everybody. And sorry, it's no longer the case that you can still guarantee 1/n of omega, but this is no longer your unanimity utility. I mean, your max mean is higher and it's not reachable. So yes, I mean, this theory is about the individual fair share going beyond those traditional contexts in which the answer was very clear. Now, to also answer the question about the assignment, yeah, the assignment is also like that. If you have an assignment problem, and even in fact, if you don't assume quasi-linear utility, but simply increasing utility in money, then you can define this unanimity utility level, and it is again feasible to implement that, and it is the solution. So that's another case in which your problem is solved. By just saying 1/n of your, in that case, it will be in the context of quasi-linear utility, 1/n of the total utility for all the objects. If you 1/n of u of A plus u of B plus u of C, where A, B, C, D are all the possible objects. But okay. yeah, the positive ortant, that's fine. I mean, that was the case where every object is good, and or simply not every object is good, but every share is better than nothing, which is a bit more general, different than the configuration where objects are either good or bad. But this is, yeah, the theory applies there too, and you still have the problem that, you know, there is no easy way to define the max mean, to define the best feasible guarantee. I hope it answers your questions.
Yeah, so anyone else?
Anirban, you want to take it from there? And
Yeah, so